All right, guys, so we are going to go ahead and get started. It's 4 o'clock. So this is Nuclear Medicine 4303, Physics and Instrumentation. My name is Michael Martin, and I'll be your instructor for the course. As far as to kind of begin here, we'll just do some housekeeping things in terms of doing Zoom calls. I would prefer for you guys to show your faces. I'm not going to make a requirement because I know some people just hate doing that. But I sometimes can get really long-winded and dry if I'm like staring at nothing. I also get excited about physics and about nuclear medicine, so hopefully that we can keep it alive that way. But showing your faces is always, of course, helpful. I'm going to keep everybody muted. I tend to just start talking and go, and I'll ask some questions here and there. But if you guys have questions, I want you to just interrupt me. I have tried several times doing the whole hand raise thing. I just, for some reason, I don't see it. I get going and just want to teach. And so if you just interrupt me, I'm totally cool with that. I'm not going to be upset with you at all. So if you have a question or something comes up along the way, just interrupt me. Or if I say something that is on the slide or that's not on the slide and I say it backwards, you can interrupt me for that. I'm known to do that from time to time. And so just, yeah, feel free to interrupt me. But right now we'll keep everybody on mute. So to kind of get started, let me just give you an introduction of who I am and what's going on with me. Like I said, my name is Michael Martin. I'm the instructor for the class. So I have been in nuclear medicine for about 16 years, somewhere in that neighborhood. I actually went through Weber State's program and I graduated back in 2009. I have been doing nuclear medicine right now. So for about the first 8 years, I worked at Intermountain Medical Center in Salt Lake City, Utah. It's kind of the big mothership for Intermountain Healthcare. And I worked there and I did both nuclear medicine, oncology PET, and also cardiac PET. All three, we kind of moved from department to department. About 8 years ago, there was some management that butted heads and so they kind of split us apart. And so we had to kind of choose. And so I decided to go into cardiology specifically. And so for about the last eight years, I've been working in Intermountain Medical Center's cardiac PET unit. It's one of the biggest dedicated PET units in the country for cardiac. We have 2 cameras. We do anywhere from 25 to 30 patients a day between those 2 cameras. And so we're fairly busy. So that's where my head is involved really high now. And next semester, I'll be your instructor for cardiac, for nuke med cardiac stuff. So I'm excited for that. You'll have me for 1 class each semester. But that's me. I know what you're going through. And so I'm here to help in any way, shape, or form, even if it's not about one of my classes, just something about the nuke med program in general. I'm happy to help you. Often people ask me, they want to call me professor. I'm not technically a professor. You can call me that if you want, but it's not quite accurate. I'm fine with you just calling me Mike or Michael. If my mom's around, definitely don't call me Mike. She hates that, but she won't be, so you can call me whatever you want. If it's nice, be nice, say that. But you can call me that. If you're really uncomfortable with like first name basis, you can call me Mr. Martin. I'm fine with that. That's my dad, not me, but I'll respond. So just whatever you're comfortable with. I'm pretty relaxed in terms of what you call me as long as it's nice. So now this is the first time, so you guys are a big group of students. So I think last time we had somewhere in the neighborhood of 23. And you guys are up in the 30s this year. So big group of students, so I'm excited for that. Tomorrow we all have orientation and there's a meeting for that. So this is actually the first year that I've taught you a lecture before we've had the orientation. So sorry how that kind of lined up. They give me a schedule and say, here's when you're supposed to teach, and I kind of go with it. So I'll see you again tomorrow. My hope, if we had a ton of time, which we don't, I would let each of you introduce yourselves. I'm sure that Shane Clampett, Professor Clampett will probably do that tomorrow. So I'll kind of save that for tomorrow. So sorry, I'm the only one that gets to introduce today, but I'm excited to meet you all and you're going to we'll get to know each other over the next year or so. So with that, I'll leave that for the introduction. I'm going to go ahead and get into our class. What I'd like to start with is I'm actually going to go onto Canvas, and I want to walk through everything I put on Canvas so you kind of know expectations and what's on there. And then after that, we'll get into our first lecture. So let me get my screen shared. All right, so will you give me some head nods or just say something if you can see my canvas? Okay, awesome. All right, so hopefully you all saw my kind of introductory welcome. I wanted to put something out since I knew we wouldn't be meeting until today. So I just kind of wanted to get you started. Really, if this is the first time you've got onto class in Canvas, you're going to be okay. We're going to talk through, we're going to teach everything that you need to know. But I did talk to you about getting on Canvas and looking through the module and going through section 1. If you were able to do that, awesome. If you weren't, don't stress. Don't stress. You'll have time, and we'll have time to learn everything. So we'll kind of skip past that welcome. So over on the left, that's kind of your home screen. I went ahead and designed it to where on the home screen you would have generally everything you need to get to. So our syllabus is on there, which we'll go through. The Nuclear Medicine 4303 module is on there, which we will go through. And then I will always post my lecture slide within a couple of days of giving the lecture. Students in the past have liked printing out the slides or going along on their own personal device and making notes. So I usually share my slides a couple of days before. I try to keep up with everything in nuclear medicine, and I try to keep myself learning. And so I sometimes will edit a slide up to a few days before. So I typically don't release it to you till then. But I'll get it on there as soon as I can. That way you can have it for the lecture. You'll also notice here that there's videos. This is where I will post our lecture videos. We'll post them on here, and then you can have access to those later so you can listen back on them. So let's go through the syllabus. Hopefully you have had a chance to take a look at that. The first thing I'll bring your attention to on the syllabus is that a lot of people tend to want to email me, and that's totally fine. I'll try to get to your email. If you want to get to me faster, message me on Canvas. I have Canvas set up to give me an alert on my iPhone. And so that's the better way to do that. And you would do that right over here on this inbox. You can send me a message. You should have messaging on there, and you can pull me up and send me a message. You'll probably get a faster response there than you would using my email. However, if you forget and use my email, I try to get back with you as soon as possible. Okay. Required textbooks. The first thing I will say is I fell behind the ball apparently on this. Typically Weber will send me the next textbook that they're going to use. And we've always used the Waterstrom text. And when the new ones come, I usually get it. I didn't get it. So I am using I have the 8th edition, and in the module, I have references to page numbers in the 8th edition. As soon as I get the 9th edition, I will update the module. And get everything on there. However, this is probably I think I've had 2 texts previous to this, and they don't change a whole lot. The numbers are probably going to be accurate. But if you've gone through, has anybody had issues with the numbers being way off? I'm seeing head nods. No. Okay, that's what I thought. If you bought this book, you can use this for the program and not use the 9th edition, and you're going to be okay. But I don't want you to buy a separate one for my class and then buy 9th edition for any other class. Okay, so Waterstrom is just, as long as you have one of those, it's good for your program. So don't worry about that. Okay, so I hope that didn't cause too much problems for anybody, and I'll try to get that updated as soon as I can. The other text that I have listed is the Mettler text, which looks like this. And then there's an Janice O'Malley text that looks like this. So those are the 3 texts that I reference in the module and give you places where you can go to study and learn the information that we'll teach. And then as far as syllabus, I have the dates. I just follow the dates that Weber has given me for teaching opportunities. I know Shauna may do something a little different. She was telling me she might do things a little more weekly. I do the dates that Weber put out originally. That makes them kind of long Zoom classes, but we teach a lot in a chunk. But that's why I make my videos available, so you can go back and take a look at them anytime you want and study. So the dates listed for me are accurate here. The only date that I went off of, and I try to never do that, but if we do a lecture on October 31st from 4 to 5:30 or 6 or however long that takes, then I'm gonna get murdered by my wife because it's trick or treat time. So, and I'm hoping all of you probably have some sort of Halloween plan. So I'm actually gonna teach on the 30th. And again, I understand if you've built your schedule to have that Thursday be the day. So if you can't attend, again, I'm gonna video that one. And we'll put it on Canvas and you can watch it then. I of course want you to attend, but I'm not gonna get so stickler that you know, you guys, I know most of you are probably working somewhere and going to school and trying to do your clinicals. So it can be rough. So that's the only one that I've changed. But in the module, I kind of, or in the syllabus, I tried to give you kind of a what to do each time before we meet on class. So we meet today. I'm going to want you to complete exam 1 by the next class. I'm not super stickler on dates. If you're running into something and you're like, hey, I'm not going to get to this, shoot me a text. It's better to try to keep up, but I'm probably going to be your easiest instructor in terms of knowing that you have a life and that it's busier than heck right now. You got to try to figure it out. So try to follow these dates. I would like you to complete those exams before the next Zoom class. We're going to talk about some math quizzes because we'll go over math today that you're going to do, and I'll go to those. And then I want you to study for the next module before we meet. So when we do section 2 lecture, I want you guys to have at least looked at it so that you're a little bit familiar. The learning goes better when you do it that way. So that's how this is all designed in terms of the schedule. And then for the grading side of things, there's the 4 examinations. The questions on the exam are worth 1 point. And then the other thing I do with exams is I allow you to go back and do what we call test corrections. So if you notice right down here, I'll just read this. Extra credit will be given for correcting each wrong answer on the tests. Please write out the question you missed along with the correct answer in a reference in a book or online or wherever you can find the correct answer. Just reference that answer where you found the answer. If you do that for each one of those that you do, I will give you back a ½ point on your test. So it's a way to kind of keep your tests up. If I could think of a way to make you do test corrections, I would. Because test corrections are an amazing way to learn. Because whatever you missed, it forces you to go back, read through it, write it out, learn it. And you'd be surprised at how well you learn something by having to correct the things that you missed. So the reason I don't make them required is because it's hard for me to then give everybody a similar grade because everybody's going to miss a different thing on the test, right? So I didn't do that. I don't make them required, but I highly suggest that you do those. Plus, it's just going to help your grade, right? And then there's the 4 math quizzes. Each question on the math quizzes are worth 1 point. And so that's what your grades will be based on. Also, I do curve at the end. I don't want to pretend that I'm a perfect teacher, and I view how you guys do in the class as also a reflection on me. So I will curve grades at the end and to kind of make it fair and to make up for my weakness. So, all right, so that's all I'm going to go over on the syllabus. Let me hurry and pop over to the quizzes. So this is where—
Can I ask a question real quick?
Thank you for interrupting. Go for it.
I'm just curious how like tests are like set up. Are they multiple choice? Are they essay? Are they all the same, or are they different each time?
Great question. Thanks, Joseph. Yeah, so they are multiple choice. They're multiple choice. All of them are going to be multiple choice. So you'll be able to go through those. That is the test. You've got 4 tests. Now the math is going to require you to do a math and put it in answer. What I've done in Canvas is I've gone in there, and when we go through the math, you're going to see that depending on the decimal, how many decimal places you round and things like that, there's going to be slightly different answers. I've tried to build in some leeway. I can tell Canvas except within this range, and that's what I've tried to do. So thank you for bringing that up, Joseph. Along that topic, if you're doing the math quizzes and you're getting one wrong and you can't figure it out, I want you guys to reach out to me, and I'm going to help you. Or occasionally I find that I should have allowed that window to be a little bit larger, right? So just communicate with me. And like I said, my big concern, and I'll tell you this, you'll probably hear this more than once from me with different classes, but I really, really care about you guys learning. I don't personally care about your grade. I know you don't want to hear that because you care about your grade a lot. But what I mean by that is that I'm here to help you learn, and we will figure that out. And if your grade is in a crummy spot at the end or whatever, or you're like, man, I didn't do good on this, talk to me. We'll figure it out. We'll work it out for you. Okay? Because I want you to learn this stuff. You guys have to take boards at the end of this, and I want you to pass. So, okay, so there's your tests and then your math practice quizzes. If you click on assignments, it actually it kicks you back, and it actually has the tests on here as well. And then if you go down, these are where you'll submit your test corrections. And so I'll click into one of these. If I go in here, it should give you the opportunity to either you can put them on text right in Canvas, or you can upload a document. It should let you upload like a Google or whatever kind of file you have. So you have those two options on there that should allow you to put in test corrections. Oh, and the other thing I didn't say, if you would do for me, sometimes I get student papers, especially if they've written it out and just photocopied and put it in here, where I don't see where one thing ends and one thing begins. So if you'll do me a favor and just either make sure you number things, or at the top, what I really prefer is say, hey, there's 9 test corrections here, and then I'll go through them and I know that I'm looking for 9. That'd be super helpful. So that's where you submit the test corrections, and then also your math is listed here again. But in terms of assignments, that's where the test corrections are. Now, I don't have due dates on the math practice. If you notice in the syllabus, I wanted you to try to get them done before we meet again, but I'm not a stickler on that, because some people get the math quick and some people don't, and I don't want you to worry about that. I want you to get the math. So work with me, we'll get you through them. I didn't put due dates on for that reason. I also don't have due dates on the test corrections. The only thing that has a due date as right now is just the tests. And again, please communicate with me if those are problematic for you. And then the other thing we have listed here, of course, is Zoom. I'm assuming that you all got to this point because you're here. So all those classes are listed, the dates and times, and then from time to time I'll do announcements, and then you can access your grades as well. Okay, so that should kind of get you started and kind of give you a good introduction. I want to go really quick over one other thing that isn't listed over here, and that's the module. It should be listed over here. I will correct that. That is why I put everything on the home screen too. So if you go down, I want to go through the module with you so you understand how it functions and how it works. So the module is essentially there to help guide your study and show you where the information comes from. With the module, we don't do an independent study course for this, but the design is that, hey, here's where I'm pointing to get the information you need. And so that's why I put on here, it could be an independent study course. It's not, but it's designed to help you get all the information. I've listed the texts again, of course, and then the start of the module, here's section 1. So what this does is it tells you kind of what we're studying, and then you have learning experiences, and it points to specific areas in each of the chapters that you find that information. So what I want you to do is study this information. Here I listed completing the math quizzes again. Do what you got to do there. But this is the information you want to study that's going to help you with test number 1, along with my lecture. So again, I don't have like assignments where you're writing out answers for me or anything like that. This is just to help guide your study. I want you to study the text sections. I want you to listen to my lectures, do the math, and then take those tests and see how we do. Once we take the tests, what we get wrong, we do test corrections, relearn, that's a learning process, and go forward from there. Okay. So as you see, there's go ahead, somebody say that again.
Are the tests timed?
The tests are not timed. Nope, not timed. Thanks for the question. I didn't see who that was, but thanks. So every section goes the same way. Section 2, same thing. You can go down all the way through section 3 and section 4. The other thing I put on here at the end, just to point you in general, is that the American Registry of Radiologic Technologists. A lot of you are probably X-ray techs, I'm assuming. So if you go to ARRT's website, they publish, you can go into a section for nuclear medicine, and they publish content specified things. I try to design my classes to go along with the content, right? So that it'll list things you need to learn, and it's very general. It doesn't get very specific, but that's what I try to do is go through those. So I would suggest just pulling that up at some point and looking through what they require you to know to take your boards. And as you're learning, that's also a good guide for you to say, okay, this is what I should focus on as I'm learning all this information. Okay, so that's why I put that there. Take a look at it. All right, I am done with the introduction of section. I don't have anything else I want to share with you right now. Are there any questions related to getting started and to the class specifically? Okay. If any of you let me check this out here. If any of you put anything over on the chat, I'm totally cool with that. But you might have to say, hey, there's something in the chat. Because sometimes I'm not paying attention. Like I said, I'm on my slides. So, all right. Let me get my slides pulled up and we will get going here. All right, can you guys see my slides? Okay, I'm seeing some nods. Okay, let me grab a quick drink. So the other thing I was going to tell you, most of I try to keep everything to the hour and a half that they've allotted us. There's been years that they've allotted me an hour and a half, and there's been years that they've allotted me 2 hours. So I try to do my best. What I would do, and again, I know you guys are tired. You've had a long day. So I'm going to start now. I'll probably give us a break somewhere in between. We're slated to end at 5:30. If you guys, when 5:30 comes, I'll acknowledge that. And if you need to leave, you can. If I'm not done, I will stay on and finish. You are welcome to stay on and finish because I want to have the whole recording in one piece. But if you need to leave because you've made plans, you have family, all that kind of stuff, you're not going to be docked for leaving when that time comes. But I'm going to finish either way. And that might be especially applicable today because we had all that introductory stuff. Okay. Looks like someone did ask the chat. Just pop it in real quick. Did see it this time. Oh, you guys are making plans. All right. All right. Okay, here we go. So today what we're going to cover.
I had a kind of random question before you get started.
Go for it.
So I started the section early and I the first quiz I did easy and then the second quiz came up. Is there any supplemental YouTube videos or anything that you recommend?
Are you talking about for the math?
Mm-hmm.
Yes. In fact, I'm going to post a video. I have a section of a previous teaching that I just grabbed just the radioactive decay equation. And so I will post that on Canvas right after this meeting. So you can access that. I also, as we're doing that section today, ask me questions. Also, I'm going to kind of give some tips on things that I know are on the quiz. So yeah, hopefully we'll answer it that way. I'm sure there are things online. Hopefully I can answer most of your questions myself. So we'll see. But good question. Thanks. Okay. So today's physics and math. I actually used to start out with the math. And by the time we got to the physics, everyone was like, their head was going to explode. So I'm going to start with the physics because it's way funner. I love it. I don't know why you all got into nuclear medicine, but I'm a geek. Like that's part of the reason why I got into nuclear medicine, because I'll just admit it, I'm a nerd. I geek out on physics. I love it. Like I love the physics side of nuclear medicine. It's so cool. I love helping patients and all that stuff. Like that's part of why I went in there as well. But the physics part of nuclear medicine is just really cool. So we're gonna just talk about kind of the basic physics of nuclear medicine to start out, and then we'll get into the math at the end. Okay, so this graphic, I wanted to start with this graphic because this kind of shows us, I love how this teaches us the size and scope of what we're dealing with in nuclear medicine. So what you want to look at here is you've got 10 to the 0. So if you work by tens and exponents, right? So 10 to the 2 is 10 times 10, which is 100. 10 to the 0 is 1, and we'll talk about a little bit more about that later. But you've got a man right here who's about 6 feet. So he's a little less than 10 to the 1, right? And so if you go up, and we go up the scale and we go all the way up to the size of our galaxy, right? You have our Earth, solar system, galaxy. You're up here somewhere around 10 to the 21st. Okay, and so I want all of us can kind of look at the sky at night and be like, man, the galaxy is huge, right? And we can't even see everything. And it's just massive. And if we measured that, that would be 10 to the 21st. Okay, so that's how big things are. But in nuclear medicine, we go small, right? So let's go the other way. If you notice, you come down to the nucleus of an atom, and by the time you get down to each individual nucleon, which is like protons, neutrons, and electrons, which we'll talk about today, you'll notice that those are as small as our galaxy is big. So to me, that's just mind-blowing, right? The stuff that we use in our field is almost incomprehensible. To me, the galaxies is just hard to even comprehend. The nucleon is that small, right? That's how small things that we're dealing with in nuclear medicine. So I just think that's really cool. Now, when I remember when I first got into X-ray, and I was learning about kind of how X-rays work, and I was learning about the atom. Someone told me, I used to wonder, how can X-rays, and we're going to talk a lot about gamma rays today, how can gamma rays penetrate a body? Like I'm totally solid, right? And someone once told me, it was one of the teachers I had, they said that if you took a basketball and you made the basketball your nucleus, that the first electron in the case shell would be 2 miles away. And all of a sudden I was like, boom, right? Like I get it. That's how X-rays can pass through me. Like there's a ton of space here. And so even though it's so massively small, there's actually a lot of space within that smallness. So anyway, just cool stuff, blows my mind. Same thing here. These are just kind of gee whiz facts. These will not be on your test. But if you took all the people on Earth, counting one atom each second, it would take in excess of 30,000 years to count the atoms in a drop of water. Okay, so like, boom. There are more atoms in a glass of water than there are glass of waters in all the oceans of the Earth. So it's just kind of crazy how big things are that we deal with. All right, so in nuclear medicine, we work with energy. And if you think about energy, I want to first bring your attention to this energy spectrum that we see down here, right? Energy comes in a sinusoidal pattern, which means that's the wave that you see, right? The one we're most familiar with is visible light, right? When you and I, our eyes work because of light, we can see around because of light, I can see my computer screen because of light, but all light is energy, right? And so energy is a product of wavelength and frequency of a sinusoidal pattern, okay? So when we talk about wavelength, we're talking about the size of the wave, the length of the wave. When we talk about frequency, we're talking about how often does it cross the middle, right? So how often does that wave come? The greater these have an inverse relationship, but the greater that frequency comes, you're going to have higher energy, right? And so what I want to bring your attention to here really with this slide, besides understanding that all energy, all of these things are just energy, is that if you look at radio waves and you notice that the frequency of this wave is really far apart, right? Microwave, it gets a little tighter, infrared, and so on as we go up, our visible light that we see. We get here to X-ray. By the time we get to gamma rays, you'll notice that it's the tightest. Now, this sinusoidal wave is not accurate to reality, right? It's meant to be a teaching tool. But what I want you to look at here is that by the time we get to gamma rays, that frequency and power and strength of a gamma ray is so tight and it's so knit and it's so bound together that when we talk about gamma rays today, or any kind of ray we use, we actually refer to it as a photon, as if it has mass, like it's an electron or a proton, but it's not. It has no mass. It's just energy, right? So when we talk about that and we talk about gamma rays, keep that in mind, that it doesn't have mass. It's actually just energy, or you could even say light, right? A much stronger light that you can't see. So again, just something to kind of put in there to understand that gamma rays don't have mass. We're going to talk about types of radiation today that do have mass, but gamma rays do not, right? They're energy. Who can tell me, and it's fine if you can't, but if anyone wants to be brave and they can tell me, what's the difference between a gamma ray and an X-ray? All you X-ray techs, you know the difference?
Their origin.
Yes, tell me what you mean by that.
That gamma rays come from an unstable nucleus generally, and at least in our practice, we produce X-rays with our X-ray tube.
Yeah, so you are on exactly the right track. You said that gamma rays come from interactions in the nucleus, whereas X-rays come from interactions within the electron cloud. Okay, so for those of you that have X-ray, we need to shift your brain, your X-ray brain. Now we're going to, instead of the interactions that have happened on the outside of the electron with the electron clouds, we're going to come inside to the nucleus. Now we're still going to have interactions in the cloud, and it's still important. But now with gamma rays, something is orienting from the nucleus, and we'll talk about a bunch of different interactions today. So who was that answered my question?
It was me, Colby.
All right, thanks, Colby.
Yeah.
All right, here we go. Okay, so we need to talk about the three energies associated with the atom, and you may have heard this before with X-ray. But before we kind of go through the list of this, I want you to just kind of take a look at these two models over here, right? So in the nucleus of an atom, we have protons and neutrons. Protons have a plus charge, and neutrons have a net zero charge. You'll notice I said net zero, and I'll explain that in a minute. And then there's kind of two ideas with how to look at an atom. You've got the electron shells that are on the outside. There are models where this looks like a universe, right? Like this is the sun, and you've got planets circling around. Those would be your electrons. There are other models where they say it's more like shelled and clouds, and that they're not necessarily circulating, but they're moving and they have energy. For nuclear medicine, it doesn't really matter so much which one you use. Both will work. But those are kind of the ideas behind those. But we work with the protons, we're going to work with neutrons and electrons. And so I mentioned plus charge, net zero charge, and then electrons have a negative charge. So let's go over to these three energies associated with the atom. So the first one is the strong nuclear force, or you'll hear it called nuclear binding energy. This is the energy that holds the nucleus together. It's one of the strongest energies in the universe at short distances. Okay. Holds those together like kind of like glue. However, if you were able to separate the protons and neutrons a little bit, it loses that pull within a short distance. So super, super strong right there inside that nucleus. Okay. The second one is electromagnetic or electron binding energy. And this comes from the positive and negative charges that attract electrons to protons. Okay. So remember, protons are in here, they have a positive charge, electrons are a negative charge. So the electron binding energy is that attraction between the protons and the electrons that bring it in. Now, we're going to talk about different nuclides today and different atoms. And the more protons, as you can imagine, more protons in that nucleus are going to mean that positive charge is a lot stronger. Okay. So each one of these shells, you have to start out with your K shell, L shell, M shell, and they move on depending on the atom. These shells are each going to have an energy level associated with them that electron binding energy puts upon them. And it depends on the amount of protons. When there's more protons, that means those electrons are more tightly bound. We call that characteristic of a particular atom, because every atom, different atoms are going to have a different amount of protons, and they're going to exert a different energy per shell. And for that proton, each of those energies is definable. We'll be able to say, okay, a K shell atom has this much energy, or a K shell has this much energy on a certain nuclide. So we'll get into that. So we call that characteristic. Now you may, in X-ray, I've talked about characteristic X-rays, and we'll refer to those a little bit. And those are because each of these shells has a certain energy level that it maintains. The last one we're going to talk about is kinetic or centrifugal. And the kinetic and centrifugal is the motion of the electrons. Again, if you want to use the orbit one where they're moving in an orbit, or if you just want to say they're a cloud and moving, electrons have kinetic energy. What I want you to remember about electrons is that the closer the electron is bound to the nucleus, it has a certain energy. It has to give up more of its energy to go down and stay in that shell, okay? So electrons, when they're closer to the nucleus, they gave up more of their kinetic energy, right, to be there. But their binding energy, the electron binding energy, is much, much stronger on that electron. So again, strong here, binding energy is strong. The electron had to give up more of its energy to be there, so it has less kinetic energy. More kinetic energy on electrons out on the edge, but they're not bound to the nucleus as strong, okay? Those are going to become important as we talk about the different types of radioactive decay. All right, so in this chart, I want to talk about the individual parts of the protons, neutrons, and electrons, and I want to talk about some of their characteristics, because how they act and what their characteristics are going to have everything to do with how things behave in radioactive decay. So first thing I want you to look at is particle or energy. Now remember, I mentioned gamma photons are energy, right? When we're talking about subatomic particles, they are a particle. In other words, they have mass. So I've put a P in the top of this chart. They're a particle. They're not energy, right? Now you'll notice on the mass, and we'll talk about this more, but a proton and a neutron are very similar in mass, whereas an electron is a lot smaller in mass, okay? Protons have a plus charge. Neutrons have a net negative charge. They actually carry, and this might be new to you, but they actually carry a plus and a minus, and we will get into detail what I mean by that and where that's important. But they actually carry a plus and minus, which is why they're neutral or net zero charge. And then the electron is a negative charge. Now, one of the things I want you to understand here is even though our mass of a proton or neutron is really large compared to an electron, these charges are the same. In other words, if I had an electron and a proton, he has a plus charge and a negative charge, the proton's charge isn't greater or stronger just because it's a proton, right? The charges are the same, the mass is different, okay? And so I put the charges right down here. And then physical function of what each of them does. A proton is what determines the physical characteristics of an atom, okay? So what I mean by that, and we'll go over this more, but it determines what the atom is. So is your atom technetium? Is your atom fluorine? Is your atom xenon? Is your atom iodine, right? All, in order for an atom to be something and have a name, it has to have that amount of protons, okay? So that's the physical characteristic. It determines what atom it is. The neutron number determines nuclear stability. We're going to go over this in more detail, so I'm not going to fully explain it right now. But just remember, neutron is responsible for nuclear stability. And then the electron is responsible for chemical properties. So if you've ever taken chemistry class, you know about interactions with electron shells and with the different electrons and how they work together. So chemical properties. We won't talk about this a whole lot. You could talk about this maybe in a different class, in your pharmacology class maybe. We'll focus mostly over here on these two in terms of function. Now, When you look at, I want to identify, when you look at the periodic table, and we'll also look at a chart of nuclides, I want you to understand what the different symbols and things mean and how we can identify those. So the X here in the middle identifies, it's the atomic symbol. It identifies what it is. So if this were, you know, a different element, it would have a different letter there. And you'll see those. So technesium, which we use in nuclear medicine, that's where the T comes from, the TC, technetium, okay? Now the Z is your atomic number or your protons, okay? So Z number is the protons. So the Z number, when we look at the Z number, that's how we can tell that it is the atom that we're looking at, right? Because again, physical characteristics are determined by the Z number, and that represents the protons. The A number is the mass number, and it represents the total number of protons and neutrons. So the total number in the nucleus is your A number, okay? So protons and then total number. Sometimes you will see a neutron number to the right subscript. It will be, over here it's represented as N. There'll be a number here. This is not always there. Like a lot of times this N is not there because they won't include it, because if you know the proton number and then you know the total of everything, you can infer the neutron number. So that's not always there. We don't really pay attention to it a lot in what I'll teach you today, but we will pay attention a lot to the mass number and the atomic number. You need to know that Z represents protons, the A represents the total mass number, so protons and neutrons, okay? All right, so now we're going to talk about nuclides. So nuclides represent some variation of an element. I know that sounds super vague, but we're going to talk about how, for example, technetium has many different forms of it and different nuclides. Nuclides, some nuclides are stable and some nuclides are radioactive. And so we're going to talk about the different types of nuclides and how we identify nuclides, and then we'll look at a chart that has the nuclides on it. So the first thing we want to talk about is isotopes. Now, if you've gone to clinicals so far, some of you may hear text say something like, we're going to inject you with a radioactive isotope. So this is what they're talking about. That's not always accurate. You're not always using an isotope, and we'll kind of define that here, but you're always using a nuclide. We always use a nuclide of some form. So in other words, again, it's a variation of some element. So isotopes have the same number of protons, but varying number of neutrons. So when we look at isotopes, you'll always have something that's called by its name. For example, and these may be stable or radioactive. So TEC is a good example of this. In nuclear medicine, we use TEC-99, okay? TC-99. That 99 represents your mass number when it's after, like it is here. It's the number that on the previous one was up here in the upper right, the A number, right? So that represents your A number. So there's TEC-99. There's also a TEC-98. There's a TEC-97. And not all of them are radioactive, and some of them are. But what you want to pay attention here is, remember in the previous slide, I said that protons identify the element. So as long as you have the same number of protons, you will never have a different element. So let me ask this question with what I just explained. Hopefully that was clear as mud. But if we go from TEC-99 to TEC-98, did we lose a proton or did we lose a neutron?
A neutron?
Exactly. That's exactly right. We lost a neutron. That's why the mass number, the total number, went down by 1, right? Because if we would have lost a proton, we'll be talking about something different, and it wouldn't be an isotope, right? All isotopes are going to be the same element. They're based on number of protons, okay? I meant to underline this P. In fact, this is the first time I've noticed this slide does not have a P underlined. Just remember that isotope, the P, represents protons. Protons don't change. It's a way to remember that, okay? All right. So all elements are going to have one or more isotopes, variations of themselves. The next nuclide that we'll look at is isotones. This is kind of the opposite. It has an equal number of neutrons, but different number of protons, okay? Remember, protons define the element, so when we have a different number of protons, it's now a different element, but they share in the number of neutrons, okay? It's a different element, but share in the number of neutrons. Again, I highlighted the N here. Remember, isotone, number of neutrons. Isotope, number of protons. The next one is isobars. So isobars have different numbers of protons and neutrons, but the total number of nucleons, or the mass number, which is the A number, is the same. So this is why I put the A, I highlighted the A here. So you can remember isobars, you're going to remember that the mass number, which is represented by an A, is the same. So these are nuclides that have the same number in their nucleus. And then the last one is isomers. They have the same number of protons and the same number of neutrons. The only difference is that there is energy contained in the nucleus, differing amounts of energy contained within their nucleus. And we'll explain this more when we talk about gamma rays, but there's different energy there. We refer to this as metastable, and I will teach you more about that in a few slides, so don't worry about defining it right here. But this is a good way to remember this, is that isomers are metastable, and so I highlighted the ME for metastable. Tech99, we call it Tech99M, is what you'll refer to, and that M denotes the metastable, and we'll talk about what that is later. So again, isotones, isotopes, isotones, isobars, and isomers, and the ways to remember them. So learn those differences and remember those. Those will definitely be on your test. All right, so now I want to talk about what is it that makes something radioactive? We need to start talking about what makes nuclides radioactive versus just being a nuclide, okay? And this chart is going to help us start to define that and talk about it. Now, to kind of show you how this chart works, so on the kind of the x-axis down here, you have the number of neutrons, okay? And then on the y-axis, we have the number of protons. What an atom wants to do is it wants to have a number of neutrons and protons that are balanced, okay? It wants to have those forces within the nucleus be balanced. One of the reasons for that is that protons have a positive charge. What one of the jobs of the nucleus is that if those positive charges, if any of you have ever grabbed two magnets and you flipped them to the positive side and tried to push them together, what do? They repel, right? They push apart. So if protons were allowed to just be right snug next to each other, they would want to push apart, and that would get rid of that nuclear binding energy that's strong, that nuclear binding, and it would push things apart, right? If we didn't have neutrons in us, then I don't know if we'd really explode, but in my mind, I think we would just, boom, we'd be apart, right? So they want to maintain that stability. That's why on a few slides earlier, I said neutrons are in charge of stability within the atom, okay? So what we want to look at here as we look at this chart is there's this 45-degree line going all the way up. What this line would represent is that for every one proton, there's a neutron, and they're matched up. So if we go up here, this line is called the line of nuclear stability, okay? And it curves all the way up. Here in a minute, I'm going to show you a bigger picture of this, but all of the nuclides are actually located somewhere along this line. What makes something radioactive is when that ratio of neutrons to protons gets out of whack and there starts to be more protons and not enough neutrons to create stability between those protons, okay? So when we have atoms that their mass is very small, their mass number, again, that A number is small, everything's a 1-to-1 ratio, but you'll notice that our line of nuclear stability up past about 38 starts to bend and curve towards the neutron side. The reason for that is that as you get bigger and bigger atoms that have more protons and neutrons in that nucleus, the more protons that are there, start to exert such a force that there has to be a greater number of neutrons to, again, keep them at a safe distance apart, that everything's happy. When that is out of ratio, when there's a problem, that is when we start to get the nucleus doing something to get rid of that, and that is radioactive decay. We are going to identify several different types of radioactive decay that you need to know, but that's essentially what's happening is the proton-neutron ratio is getting out of balance. And so that atom or that nuclide is trying to get to a stable state again. Again, that's why neutrons are in charge of nuclear stability. And when they're not stable, the atom is going to start playing around and moving things around to get to a stable place. So that's what this chart represents. And that's why it kicks to the neutron side, because you're going to need more neutrons as we go along. Now, if you follow the line right at the middle, everything that goes right up the middle of this are stable atoms. That black line represents stable atoms. Everything below that black line has too many neutrons, so the nuclide's got to do something to fix that. Everything above the line has an excess of protons, and so the nuclide has to do something to fix that, and that's where radioactive decay occurs. Okay, so let me give you a better view of this, an up-close view. So I'll first bring your attention to the chart up here. They actually call it a stability belt. And you can see that this chart, each one of these boxes represents a nuclide. And so they have this belt, and all the stable ones are kind of up that middle belt. And then everything unstable, you'll notice that somewhere right up above about 130, there is nothing stable. They're so heavy that they've got to do something to get back to a normal state. So everything above this line right about here, which is about 130, is radioactive. Below that, again, about 38 or so, you kind of follow the 1-to-1 ratio, and then you get really heavy on the neutrons. So that's what you're looking here. And you can see that it's defined right here as a stable nuclides or radioactive nuclides. Down here on the lower left, I know that this looks a lot like the periodic chart. It's not the periodic table. It just looks like it. What this is right here is a blown up section of this curve where we've blown it up. Okay, and it allows us to look at it. And so a lot of the stuff you see on here is defined in some similar ways to what you see on the periodic table, but different. This is where you can see the type of nuclide that it is. What I want you to, before I explain deeper here, I want you to look over to the right-hand side in the lower left, or lower right. A minute ago, we learned about isotopes, we learned about isobars, and we learned about isomers. This chart is arranged according to isotopes, isotones, and isomers, okay? So everything going horizontal on the chart like this are all isotopes of each other, okay? If you come back over to this other picture, you'll notice tech, right? Technetium. Here's technetium-99. That's you probably use that 90% of your time in nuclear medicine. And you notice you got tech-97, 98, 99, 100, 101, right? Because those are isotopes, so they're going to be located horizontally on that axis. The next thing you have is the isotones, okay? Isotones are coming up this way, right? And remember, they have the same mass number, or excuse me, the same proton number. You can clearly see they don't have the same mass number. Same proton number. I lied to you. That is not, hold on a second. Isotones. They don't have the same they have the, no, they have, oh, that's, sorry. Whoa, sorry, I worked a whole shift today. Right here, and it's defined right here. You can see it. So these have the same number of neutrons, sorry. If I looked at my slide 2 slides ago, I would know what I just taught you. So number of neutrons. So you got same number of protons, same number of neutrons, so isotones. And then coming at the angle, you have the isobars. Okay, so that's where you're going to see the same mass number, the same A number. And you'll notice that you've got tech and you've got rubidium, but they're both 99. So rubidium, tech, molybdenum 99. We'll talk about those more later. But that's how the chart is put. You've got the isotopes, you've got the isotones, and then at the angle you have the isobars. And we will, as we get into radioactive decay, we'll reference this chart again. Sorry for my brain there for a minute. I do that every once in a while, like I told you. Call me out if I do it and I don't catch it myself, call me out. Okay, so now we kind of have a foundation for what makes a nuclide radioactive. Now we need to talk about, remember I said that nuclide is going to try to do a bunch of things to get stable again. So we're going to talk about radioactive decay. Now there is more radioactive decay than radioactive modes than what you see here. But these are the ones that we're going to talk about in nuclear medicine, the ones that will kind of matter for nuclear medicine. So we have alpha decay, beta minus, beta plus, electron capture, and then gamma ray emission and internal conversion. So we'll start with alpha decay. All right. So alpha decay happens on that far right side of our belt, of our curve that we looked at. And you'll notice here, these are really big nucleuses, big atoms, they're heavy. These are atomic numbers greater than 150. So a lot of protons in there, their mass is large. What happens in here is when it's radioactive, it's that big, what it actually will do is it will kick out 2 neutrons and 2 protons. You will see in your book, this is sometimes called fission. I would know it under both names. I could see your boards asking you that question. They could identify it as fission. Mostly I hear it as alpha. That's what you're going to hear mostly, but again, it can be called fission. It kicks out 2 neutrons and 2 protons. An example of this is radium-226, which is an alpha emitter. When that is kicked out, you get an atomic number that is reduced by 2 because we got rid of 2 of our protons. That's your Z number. But your mass number is reduced by 4 because we got rid of 2 protons and 2 neutrons. Okay. Now, if we get rid of those, you're going to notice that you end up with a different nuclide. So when you have alpha decay, it starts as one thing, emits, and becomes something else. We call that a daughter-parent relationship, and we'll mention that on several of these. The thing I want you to remember about an alpha, besides that it kicks out the 2 protons, 2 neutrons, is I want you to remember that it's very large. So it's in tissue, alpha particles are very damaging because they're so big. However, they're very, very big, but they're very, very weak. What I mean by that is they don't have much travel and they don't have much penetration power. So you can actually use a thin piece of paper to stop an alpha particle. But inside the body, when it's ionizing tissue, it's very ionizing. Whatever it's next to is highly damaged. It just can't travel very far and move very much. Okay. I think of like if you were to go and you saw a frozen lake and you had like a huge rock, you know, if I found like a 300-pound rock, I'm not gonna be able to lift it or move it much, but if I threw it through the lake, it's going to be very damaging, right? But it just doesn't move very far. It only travels a few micrometers in tissue. It's not useful for imaging. We don't image alpha decay in nuclear medicine. However, one thing that it's useful for in nuclear medicine is its treatment of metastatic bone pain. So radium-226, there's a treatment called Xofigo. And what they have is patients who have metastatic bone disease. They're not trying to necessarily cure, but reduce pain. You can send Xofigo in and it will go and it will attach to areas that are causing pain and it will kind of kill off some of that tissue and reduce the pain for patients. So people will get Xofigo treatments and it's an alpha decay that they use for that. Next one is beta minus, okay? In beta minus, what you have, and I'm going to try to give you some helps to remember some of these things, but in beta minus, what you have is you have a nucleus that has too many neutrons, okay? So it's on the lower half of the curve, right? It's radioactive because there's neutron excess. So we have too many neutrons, we need to get rid of some of them to get back to the stability. What I want you to remember about this when you're memorizing it is that you notice that there's negative, it's beta minus, okay? And that neutrons, you'll think of neutrons are neutral, they don't have a charge. When we talk about beta plus, we're going to talk about protons, but negative, beta negative is spelled with an N, and it's neutron excess, right? So you can measure up the neutron and the negative. That's how I remember it. Hopefully that doesn't just screw you up, but I think that's how I think of it. Neutron excess, beta negative, beta minus, it's a negative sign, so it has neutrons, the ends match. So this is neutron excess. What happens in beta minus is the neutron is transformed into a proton and an electron. The proton stays and the electron is ejected. Now, this is why earlier I said to you that neutrons have charge, they just have a plus and a minus, which makes them a neutral charge. This is why beta minus can happen, is that when that is unstable, the atom can get rid of some of that, it can change the configuration by getting rid of the negative charge out of a neutron. That negative charge goes out in the form of an electron. So that's what you kick out in beta minus, okay? Is you'll get that electron coming out. Now what happens, because we've created another proton, do we have the same element still? You can shake heads.
No.
No, that's exactly right, because protons identify the element. So now we have a different element, right? So they've changed. The atomic number, the protons have changed. That should say, yeah, atomic number. I'm tired, you guys, sorry. Atomic number is the Z number, and it increased by 1. So now we have more protons, we have a new element. This is what you call a parent-daughter relationship, okay? So in this case, the parent, here's a good example, and you'll learn about this in your pharmacology class. We get technetium-99 from molybdenum, okay? So molybdenum-99 is a beta emitter, and it'll emit the beta, and then it becomes tech, right? And you'll notice, if we go back, you'll notice that relationship right here. And I think I'll point this out in another slide as well, but molybdenum decays by beta and becomes tech. So there's this parent-daughter relationship, right? That's what it decays to. And you can see that relationship here, these parent-daughter relationships. We call that transmutation. Remember transmutation. That's probably something that could be on boards, maybe one of my tests as well. Understand what beta minus is. When we go from a parent to a daughter, it's called transmutation. We've changed into a different element. So neutron excess, beta minus gets rid of the electron from the neutron, becomes a proton, and then changes to a different element. Now, this electron is the radioactive decay portion. This is where the energy comes from. It comes out in the form of an electron. It travels about 1 centimeter in soft tissue. So this is smaller than alpha, right? It's a smaller particle. It's not that big particle of 2 protons and 2 neutrons. It's just an electron. So mass-wise, it's smaller. And whenever we have smaller mass, we're talking about less damage within tissue. However, it has more power to push. It travels further. So this will travel about 1 centimeter in soft tissue, okay? So this is actually useful for some nuke med applications. One of those is I-131. So we use I-131, give that to a patient. For patients that have hyperthyroid, we can give them I-131. The thyroid attracts the iodine and pulls it into the thyroid. And then that beta minus kills off some of the thyroid tissue and takes that hyperthyroid patient and brings their thyroid back to a more stable place where it's not so hyper, right? So we do treatments with I-131 because of that beta. That's what we're using. Now, we don't image a beta particle, okay? We'll talk later about I-131 and how I-131 actually has a gamma that's part of it too. We'll get to that in a minute. But for right now, when you think about this, I just want you to think about beta minus is that little electron coming off, not useful for imaging, but we do use it in some treatments like I-131. Okay, the next one is beta
Question.
plus. Yep, go ahead.
So basically, it's a neutron turns into a proton, and that sheds the electron that kind of was making it neutral. Is that kind of right?
Yep, that's exactly right. just all I want you to remember from that is that you had an excess, just remember excess neutrons, so we got to do something to get rid of a neutron and get the ratio more like it wants it. So again, it took that neutron, it broke it into a proton, because again, remember, neutrons have plus and minus charge. So the plus, retaining its plus charge, it simply becomes a proton. It's now plus in its charge, gets rid of its negative charge in the form of an electron.
Okay.
Okay?
Thank you.
No, thanks for interrupting me. All right. So now we'll do beta plus. This is kind of the inverse of beta minus. Sometimes this is called positron decay. So with beta plus, we have a proton excess. So again, a little, the hook to remember again is when you're doing beta plus or beta positive, plus rhymes with proton. So just remember that. Beta plus, I got a lot of protons. So now we got to do something to change that, the fact that we have too much protons, okay? So in this case, what happens is a proton transforms into a neutron by giving up its positive charge in the form of what they call a positron. All a positron is it's an electron that has a positive charge. Now, if any of you out there have had any basic physics before, you might be like, wait, that's not right. That doesn't exist, does it? It does. It's called a positron. And the reason we don't talk about them a whole lot is because they only exist for a very fraction of a second. They're very, very quick. They don't last very long, because what happens is when the electron is ejected out of the nucleus, it will go and it will find a free electron. And what will happen is what's called an annihilation reaction. That positive and negative will be attracted to each other at such great force that they do what's called annihilate. They have an annihilation reaction. They hit each other with such force that their mass is actually converted into energy. So this is E equals mc squared from Einstein, right? Their mass actually becomes energy. So both of those get annihilated, and what you end up with is two photons, two gamma photons, traveling apart exactly opposite at 180 degrees. Those photons, this chart says 5 MeV. You won't hear anybody say that. They say it's 511 keV, just a matter of decimal places. So 511 kiloelectron volts traveling opposite. This is what we image in PET, okay? So in PET, we don't image the positron itself. It goes out of that nucleus, annihilates. What we image is the two photons going directly apart, 180 degrees opposite. And when we get to PET in our last lecture, we'll get more into the physics of how that works. But that's positron emission tomography. That's what PET stands for. But we're imaging the energy that comes off of the annihilation reaction, not the beta plus or the positron particle in PET, okay? So again, proton excess. The proton becomes a neutron by giving off its positive charge in the form of a positive electron. Now, there's also, in fact, and I didn't explain this earlier, but let me go back. Well, I'll finish this slide and then I'll go back to one other thing that's on the slide just so you don't get confused. But the neutron stays, the positron's emitted. Again, because we did that, we changed our proton ratio number. So again, we get transmutation, we have a parent and a daughter, there's a new element created, okay? So a new element happens there. This requires energies of 1.022. The way that you get that is that an electron has a mass. When they look at it, it's called AMU, or a mass energy unit. Don't worry about that. But it has mass of something that's measured at about 511. And so when those two come together, it creates this excess, this energy of 1.022 mega electron volts that again split apart into the 511 kilo electron volts, or you could say 0.511 MeV. This is again useful in PET, okay? So that's beta plus. Now, what I wanted to show you, and I forgot to tell you on a previous one, but if you look at this beta minus, and I listed this on here, but you'll notice that this chart, it has the proton coming out, it has the proton being created and the electron coming out, and then there's something that's called a neutrino represented here. You don't have to worry about neutrinos. Essentially what happened is when and again, scientists change their view of what happens from time to time and what's actually in the atom. But what happened is if you measure that neutron before the proton and the electron were created, if you measure its mass, and then you measure those two separately, they don't equal the mass of the original neutron in terms of weight. And so the explanation that is in science right now is that there's something called a neutrino. The neutrino doesn't do anything. It supposedly doesn't interact. And it's just kind of their latest explanation for the difference in the mass, right? Only reason I put it on here is because it's in your textbook and it's also on this chart. You are not going to be asked a question about neutrinos in my test, and I guarantee it's not going to be on your boards. So it's included in there. Don't worry so much about that. On the beta minus and the beta plus, there's neutrinos created. All I want you to remember is, again, what we have excess of, what it does to change with the electrons and the protons and the neutrons, and get rid of that excess energy. Okay, don't worry about the neutrino. Hopefully I didn't just confuse the heck out of you. You can watch it again. Okay, so the next one is electron capture. So this one is also a proton excess. Okay, so we're still dealing with excess protons. And what can happen in this one is that to change that and to get back to a stable state, the nucleus will actually basically reach up and grab a K-shell electron, and it will pull it in. Okay, that electron, because we have proton excess, that negative is combined with the proton, and that form changes it into a neutron. Okay, so again, we're changing our proton number again. So that will change, and usually it's in that K shell because it's the closest shell. It'll grab that. Now, one thing that you get with electron capture, and we'll talk a little bit more about it, the importance of it later, but you're going to get what are called characteristic X-rays. And I know a lot of you are familiar with that because of X-ray. But essentially what happens is when this K shell leaves a vacancy, an electron in a shell above will come down and fill the vacancy, and it will cause a chain reaction of all the shells coming in and filling electrons. When that happens, that electron gives off energy, and that's that binding energy that it has to the atom. It gives all of its kinetic energy up, and it gives off what are called characteristic X-rays. Okay, and so you'll get some giving off of X-rays with electron capture, and we'll see that when we sometimes when we image, we have to do things to make it so that we don't image those. And then also in this process, when that electron comes down into the nucleus, it can actually just excite the nucleus, and that excitation can be given off as just gamma rays sometimes. So it's trying to get stable, and in the process gets really excited, gives off some of that energy in the form of gamma rays. So with electron capture, you kind of have a few different things happening and going on. The element changes, and that gives off a little bit of gamma rays, a little bit of a characteristic. So electron capture isn't the best. I-123 is one of the things that decays by electron capture. And I listed that one because you can image, because this gamma, we can set the camera to look for that gamma ray coming off I-123. So you can image it. I know a lot of departments will do their therapies with I-131 and getting that beta where, to ablate the thyroid or whatever. And then they'll image with I-123, they'll image the thyroid because it has that gamma ray coming off. So one thing to keep in mind, and we'll further explain that here in just a little bit, is that sometimes some nuclides can have a beta, and they can have gamma, and they can have multiple things happening at one time. And electron capture is one of those examples where you have a couple of different things going on. Okay, last one, and then I'm going to give you guys just like a quick break. So the last one is isomeric transition, and then we'll talk about something called internal conversion. Now, isomeric transition is just gamma emission. The book defines it as isomeric transition. If you hear people talking about this in the nuclear medicine department, they're just going to talk about gamma rays, gamma emission. That's what it is. The book, I think, will define both. Anytime someone says gamma rays, just know that they're talking about isomeric transition. Okay, So what's happening in isomeric transition is that this is one of those instances where there's nothing happening in terms of the radioactivity being off in terms of the proton neutron ratio. What's happening here is you just have an excited nucleus that usually it's from something else that just occurred, and it gets really excited and it needs to give off that energy. And that's where we get gamma rays from, right? And mostly gamma rays are what we image in nuclear medicine. Okay, so this is our big thing that we do is image gamma rays. So this comes from an excited nucleus with excess energy, no change in protons or neutrons. That nucleus will radiate that electromagnetic energy in the form of gamma rays. Now, particular isotopes emit different energies and can be identified on the basis of the gamma ray energy. Okay, so different isotopes, and a lot of that depends on how big it is and the protons and how strong that nucleus is, but they give off different energies. And so you can actually take, if you have something and you can measure that it's radioactive, but you don't know what, maybe you have a spill or who knows what, you're measuring radioactivity, you can actually determine what nuclide it is by putting it under a spectroscope. And a spectroscope will actually identify the energy coming off. So we can measure the gamma ray energy and we can know what nuclide we're looking at. So for example, technetium-99 has a 140 keV gamma. That's the gamma that it gives off. So if you put some radiation under a spectroscope and it came up and said, we're reading 140 keV, you know that you're looking at technetium-99. Okay, so another example would be like I-131. I-131 gives off a 364 keV gamma. So you could say, I know that's I-131. And we'll learn in our next lecture when we talk about the camera, we're actually going to use that knowledge to tell our camera the energy that we want it to look for. We can tell our camera, we want you to look for 140 keV and ignore anything else you see. And that's part of how our camera is going to function. So we'll talk about that later. But just understanding gamma emission, it's just energy, and every isotope gives off a certain energy. Now, one of the things that happens within gamma emission is something called internal conversion. Internal conversion is not a good thing. It's not something we want, but it's something we can't avoid in gamma. What happens internal conversion is the gamma rays are coming off. Energy, as you can imagine, is coming off of the nucleus, right? We said gamma rays come from the nucleus. So it's coming off of the nucleus. And what happens is it will hit an electron in one of the shells. And when it hits that electron, it's gonna knock that electron out. And that's called an Auger electron. So what will happen is when that electron is knocked out, you're going to get characteristic X-rays. So you're going to have that same cascade response. You'll get characteristic X-rays when it's knocked out. Now, this is going to sound, I'm going to read this and it's going to sound funny and then I'll explain it better, but the kinetic energy of an electron will be equal to the gamma ray minus the binding energy of the electron shell. Let me give you an example, because it probably sounds like I just spoke gibberish. The example's down here. Technetium-99 has a 140 keV gamma that it gives off. Tech-99 emits that gamma 88% of the time. It gets out of the nucleus and we use it for imaging. We like that. 88 is a good number, right? 12% of the time, it's going to come in contact with that K shell and it's going to have internal conversion, okay? So what happens is if you have 140 keV, the binding energy of the K shell electron on technetium is 21 keV, okay? That's how much energy it has in that place. So when that 140 hits that 21 gets knocked off, and that 21 stays with the nuclide. The electron goes flying, and the rest of the gamma that's left is now only at 119 keV. Okay. The reason we don't like that is what I mentioned just a second ago. Is we're going to set our camera and we're going to say, okay, camera, I want you to look for a certain keV because I've injected my patient with technetium. It's 140 keV, and I want you to look for that. So please look for that. And the camera's going to look for 140. But 12% of the time on tech, it's going to see this 119 and it's going to ignore it, right? We need to be able to tell it what to look for and what to ignore. And this kind of reduces the efficiency and provides a photon that we're not going to use for imaging and that can be damaging in our patient. So again, we like things that have a high percentage. 88%, 12% is good. Anything that we look for that has a gamma ray in nuclear medicine, we're trying to find nuclides that have a high rate of being able to get out, right? The low rate of internal conversion, and technetium is one of them. You don't necessarily have to know internal conversion numbers on each nuclide that we use. Just understand what internal conversion is. It's some of those rays hitting electrons and we kind of lose them. It's not something we desire or want, okay?
Will it only interact with the K shell, or will it interact with the other shells as well?
Usually when you look the information up, it will tell you 12% based on K shell. It can interact with other shells, but I've never seen it. When you look up numbers for things, you'll never see it. It'll just give it 12%, and that's supposed to represent the K shell. But you could, when you on your camera, each of your cameras actually has a section on there where it represents like a spectroscope, and you can see the energies that it's seeing. When you look at that on your camera, you'll see these curves, and we'll talk about that next lecture. But sometimes you'll get a few different things, and you can kind of look and see what energies you have coming off on your camera. But for purposes of learning, I'm going to say it's just K shell. Beyond that, I don't know. Let me just kind of get a consensus of what you guys want to do. We technically only have 10 minutes of class left. If the majority of you are going to stay, then we'll take a 5-minute break. If you're not going to stay, then I might just keep going. The few of you I can see, give me thumbs up, thumbs down, maybe. Or
I'll
some-
have to bust out.
Okay, yeah, and that, so do you, if a lot of you are going to go, I'm just going to keep going from here and not do the break because
I
we
have to go.
9 minutes left. Okay, that's what I'll do. Unless anybody is really opposed to that, I'm just going to keep going. Okay, okay. Like I said, this will all be recorded so you can reference it later.
Sounds good. I'll stay as long as I can, though.
Cool, great. That sounds great. All right. Okay, so you've gotten through all of the types of radioactivity that we use and that you need to know. Okay, go back and look at those. I know it can seem kind of daunting. I remember when I was in your stage, I was like, "Whoa, what did I just learn?" You know, but go through and study it, and you'll get it. And again, you can go back and listen to the lecture. The next thing I want to talk about is decay schemes. So I mentioned earlier that nuclides will have different ways in which they decay, and those are represented on decay schemes, and I'll show you a couple of those on specific nuclides. What I want to look at right here is just kind of define what decay schemes are doing and what it means. Okay, so if you look at the kind of the chart, it's not really a chart, and you'll see I'll show you an actual decay scheme that works better. But when we're going on a axis that is vertical, that's representing energy. Now, when we talk about radioactive decay, the energy is always going to be, we're getting rid of some form of energy, whether that's mass from an actual part of a nuclide, or whether that's energy in the form of gamma rays. Anything going down is what we're getting rid of in terms of energy. And then from right to left, it's going to represent the atomic number. So you'll start out with whatever your parent is, and then you'll change to your daughter, and that's kind of how this will be represented. So in other words, and you'll get it as we get going here, but here's alpha decay represented. So when we have a nuclide and it decays by alpha, what you're going to see happening is, remember, in alpha we get rid of two protons and 2 neutrons. And so what you're going to see happening on alpha is it's going to go represent that we're losing protons, so it's going to go down into the left. Okay, so our proton number went down by 2. So that's going to be represented by losing energy to the left, right? We lost it to the left. Okay, in beta minus, again, remember that's neutron rich, so it gives off an electron from a neutron, creates a proton. So because we're creating a proton, we're going to go to the right. we get more on, again, because remember, this is atomic number, our Z number is represented by the horizontal line. So we gave ourselves more proton, and that's how our energy changed. So again, alpha, we lost 2, beta, we gain a proton, beta plus, we're going to lose a proton, because in beta plus, we're sorry, we're proton rich, and we give off a positron and create a neutron, so our our proton number changes. Okay, so that proton number goes down. Electron capture, same thing. We have proton that goes down, we lose a proton. And then in gamma emission, what you're going to notice is because we don't do anything with our atomic number, our protons don't change, you're going to see gamma represented as going straight down. The other thing I want you to pay attention to on this chart is that oftentimes in charts, you'll see an alpha particle represented as the alpha sign. And then we have beta minus represented with the beta sign, or what looks like a B with the minus. Beta plus is B with a positive. Electron capture will just be represented as EC. And then gamma emission is represented with the little Y. So I'm going to give you another chart to look at that will hopefully make this a little better. So again, in our first form of emission here with the alpha, or excuse me, this one's beta actually, beta, you'll notice we have our random nuclide. Obviously, the X is just to represent something. We have X, and we notice that we gain a proton, so our Z number goes up by 1, and we have a new element. Okay, so that's how you read these. Electron capture here, we're creating another proton, we're getting a proton, or excuse me, we're losing a proton, so our Z number goes down. Same thing here, we're losing a proton in positron emission, and then isomeric transition of gamma is going straight down. So if you see a decay scheme, this is what you're looking at. As you're looking at, it's telling you how it's decaying, by what method, and what happens based on, again, this is all of this horizontal line is that atomic number. It's all about protons, what's happening with our protons. So let's look at one. We're going to look at tech, and we're going to define now what I meant when I said metastable earlier, okay? So Tech 99, I mentioned, comes from molybdenum. You're going to learn about this when you learn about molybdenum generators and how we get tech in your pharmacy class. So it comes from molybdenum 99. And what you see represented here is that molybdenum decays via beta, okay? And it's going to come down to the right, so we're creating a proton, right? That happens 88% of the time. And that is what decays and becomes now tech. Tech decays by gamma, that's the Y represented here. Now, the 12% of the other time, there's 88% of the time that molybdenum goes to tech. There's 12%, and this is Tech 99M, and we'll define that in a minute. And then 12% of the time it decays down to, there's a G here, don't worry about the G, it's just regular technetium 99. Now, let's define metastable so the chart will make a little more sense to you. Molybdenum is a really good example of this because molybdenum gives off, you'll notice this is going straight down, so it's a gamma. So it decays by beta into tech and changes, this is again, parent and daughter relationship. This 12% happens immediately. That gamma that gives off from the excitation of that beta happening, it just gives it off immediately. Whereas you'll notice that Tech 99, you'll notice this 6.10H. That stands for 6.10 hours. So what happens is tech is what we call metastable because it doesn't instantly give off all of its gamma. It has what we call a half-life. You're gonna know what half-life. You don't already know what a half-life is. Essentially, when a gamma ray that we can measure for any amount of time gives off energy, it's the measurement of how long does it take for half of that energy to go out of the nucleus of the atom. Okay, so in this case, Tech 99 has a 6-hour half-life. It's technically 6.01, but you'll never hear anybody use that. They'll say 6-hour half-life. So when it's metastable, it just means that there is a measurable delay in the emission of the gamma photons. So really anything that's gamma and has a half-life is technically a metastable type of nuclide. It's metastable. So in this case, Tech 99 is isotope that is metastable. And this is what I meant in the first chart when I told you guys to remember Ne or isomers. Isomers are metastable. That's what metastable means, is there's essentially a time that we can measure it and it has a half-life. So that's what you're seeing represented here. This one doesn't list anything, it happens immediate. That's why there's no hour mark left next to it. It's just, it gets excited and immediately the energy's gone, right? And it decayed by that beta. This one in technetium, that gamma goes on for 6 hours. Don't worry about this. This normal tech will then decay down into rubidium-99. Don't worry about knowing that. Just understand that what metastable means is it's something we can measure for a time. And they call it metastable because it's not stable, it's radioactive, but it's stably radioactive, so it's metastable. Here's another one. This is I-131. So I-131 decays by a beta minus 93% of the time. Once that beta minus comes down, then it also gives off a gamma, and here it's listed as 0.364 MeV, mega electron volts. Working in nuclear medicine, you don't say it as mega electron volts because no one wants to say 0.364. You'll hear it as 364 kilo electron volts. So 364 keV. This is why with a thyroid, we could ablate a thyroid here with the beta particle, but you could also stick someone under your camera and get an image here with the gamma ray that's coming off. So this gives off 2. And a lot of stuff does that. It will have its normal form of decay with beta minus, beta plus, whatever, and then there may be a gamma ray associated with it. So just remember, anything that we ever image, you're imaging gamma rays. We don't ever image alpha and beta particles. And then this is where I wanted to come back to this chart so that you can see the parent-daughter relationships are represented here also and how they decay. So anything that goes, if you start with the parent and the daughter is up and to the left, you know that that's decayed by beta minus. If you start with the parent, you go down to the left, you know that that's an alpha decay. And if you have the parent and you go down to the right, you know that you've had beta plus decay, right? And that's what we notice here. So rubidium, right, is down and to the right is tech. That's a beta plus decay. It's decayed down to technetium, which is also what was represented here. That's why it decayed down to the right. Okay, so rubidium decays to technetium. So you can see parent-daughter relationships. And in fact, you notice that normal tech-99 ended up being molybdenum, which was also demonstrated here. Excuse me, sorry, I'm back. Where is it? Slides here. Sorry, I meant to say to the rubidium. I actually went the wrong way there. It's rubidium. So molybdenum's down here. The decay is by beta minus, and tech decays again by beta minus to rubidium. Sorry, I said that backwards.
I have a question.
Yeah.
So some decay over like 2 half-lives. Does it become, or so if MO99 becomes Tech-99, Tech-99's the daughter, but if it decays again to rubidium, does it become the daughter number 2, or is Tech-99 now a parent? And then
it's the parent. So Tech-99 would be the parent of rubidium-99. Molybdenum is the parent of Tech-99. So
okay.
I got my dad and then I've got my kids, and it shifts. But understand that half-life just defines the time that it takes for it to decay halfway, right? So when you say 2 half-lives, I'm a little bit leery to correct you. I want to correct you right there, because it doesn't mean that there's a half-life happened here and a half-life happened here, because tech just has a 6-hour half-life. And so if you have, like, let's say you have 20 millicuries of tech, every 6 hours it's half gone. So you have 20 millicuries, 6 hours later, it's going to be 10, 6 hours later, it's going to be 5, 6 hours later, it's going to be 2.5. So when we talk about half-life, it's within the nuclide that we're talking about itself. But when it's decayed all the way, it decays down to a different element.
Okay, awesome, thanks.
No problem. Okay, we're gonna talk about quickly. That's all the radioactive stuff. It's a lot, and I know it's a lot. So again, go in, study it, look at it again. It will come. it's a lot of stuff. This whole lecture is a lot of stuff, but just go back. I remember again, I was overwhelmed when I was in your spot. But you'll get it, and now I'm teaching it, so if I can do it, you can do it. What I want to talk, and then we'll be done with the physics, and then the I'll do the math, and again, if you guys need to go, that's fine. So we need to talk about interaction with matter. So what we've talked about so far is nuclides and their radioactive decay. What we also need to talk about now, when I say interaction with matter, I'm talking about what are some of the reactions that happen in your patients. For those of you that do X-ray, a lot of this is going to be a little bit of review, and so I'll go through it pretty quickly. I'm going to talk about photoelectric effect, coherent, and Compton, because we still have some of those interactions happening because of the radioactive decay that's occurring in our patient, okay? So photoelectric effect, what I want you to remember here is you've got an incoming photon. Now, in X-ray, you always said an incoming X-ray. Likely, for us, it's going to be a gamma ray that's coming and hitting a atom within the patient's body, right? So that's why I made that definition. You've got an incoming photon, gamma ray, coming into an atom in the body. And what's happening is it's striking, typically a K-shell strike. When that strikes, that incoming photon is totally absorbed into the atom itself. And then because that electron is kicked out, that can go and cause ionization within the body. Well, that is ionization. You've gotten rid of that electron. And in order for that atom to correct itself, it's going to have some characteristic radiation that's emitted. So now this is characteristic X-rays coming off, right? They're forming the body. So characteristic radiation is coming off because the electrons are going to go down the shell and fill, and you're going to get off radiation. So again, photoelectric is something we don't like this effect because it increases the patient dose. The next one is coherent. Sometimes it's called Rayleigh. This is where an incoming photon comes close to the nucleus and it changes directions and is scattered off. With this, it doesn't knock anything, but it just causes more scattered radiation to happen. And when we talk about the gamma camera, we'll talk a little bit about, we worry about scattered less in nuclear medicine than we do in X-ray, but there's still some effects that we'll talk about. And the last one is Compton scattering, which is incident photon comes and strikes an outer shell electron. We call that the Compton electron. So the electron goes away and the incident photon is scattered off into a different direction. It can go and do more damage than ionization. So all of those are things we want to avoid. The last one I'm going to mention is pair production. There's part of me that does not want to mention this. This could be on your test, and when you go to the ARRT content specifications, they list it there. And so I teach it because of that. You will not see this in nuclear medicine or in X-ray for that matter, because you have to have something strong enough to create what's called pair production. So let me explain. What you have happening here is an incident photon X-ray. It's not going to be an X-ray because it wouldn't be powerful enough. So this chart is a little false, but it's going to come in and strike the nucleus. And what you're going to happen is the same reaction that happens in beta plus. Okay. So you're going to have the nucleus get struck and a positron is going to be kicked out and an electron. So essentially what's happened there is either a neutron or a proton can be struck and it kicks out their charge. So in this case, a positron comes out and then you have an annihilation reaction just like you see in the beta plus, where you have the two 511 keV photons heading in opposite directions. So the difference here is that this is created by something powerful coming in and hitting the nucleus, whereas in beta plus, it's just because there's instability between the proton-neutron ratio, and the nucleus is doing this itself and giving off a positron, okay? So the reason I say you're never going to see this is because you'd have to have a 1.022 mega electron volt ray coming in. So this is probably something you could see at, like, I don't know, a radioactive power plant maybe, where you're working with something that's that strong, but you're just not going to see it. But the boards do want you to understand what pair production is. So something strong enough that's coming in that's causing essentially what looks much like a beta plus reaction. Okay. That is the end of physics, and I went way longer than I thought I was going to, so I'm so sorry. Again, as you guys need to trail off, that's fine. We're gonna go through the math. There's actually not that many slides that I'm gonna go through on the math. I mainly am gonna cover one main principle. You will have Shauna is gonna go over a lot of other math principles with you as well as she does her class with you. I'm gonna cover radioactive decay and the equation we use to figure out radioactive decay. I have a couple of principles in here that I'll highlight, but I mostly want to focus on that radioactive decay, and Shauna is going to cover most of the other math that you'll learn in nuclear medicine. So the math, luckily the math we use in nuclear medicine is algebra, so you don't have to get much more advanced in what you need for your boards, which is lucky for me because I'm not a math genius, right? Again, when I learned this, I was like, man, I got to figure this out, and I was really overwhelmed. But know your basic algebra. We need to know how to work with fractions. We need to know how to add and subtract, multiply and divide fractions, because we work with fractions a little bit. You need to understand scientific notation. So scientific notation just allows a very large number or a very small number to be represented. So if you're not familiar with scientific notation, if we had a very small number like 0.0037, we would represent as 3.7 times 10 to the negative third. The way you get that is you take your decimal and you go over 1, 2, 3 places to get 3.7. So that would represent 3.7 times 10 to the negative third, because we're going small. If we're going big, like a number like 37,000, we do 3.7. This would be times 10 to the fourth. So we're not negative here. And the way you figure that out is you would say, you would take your decimal, which is here, and you're going to go to the positive. You're going to go 1, 2, 3, 4. And so it'd be 3.7 times 10 to the fourth. So just kind of understanding what you're looking at when you look at scientific notation. Again, we're just representing large numbers in a way that we can work with them. And then in just generally on exponents, understand your 10 powers. 10 to the 1 would be 10, 10 to the 2 is 10 times 10, which would be 100, and so on and so forth. 10 to the 0 equals 1. Again, just some algebra principles to refresh on. Understand prefixes. I've highlighted ones that are important that we use a lot in nuclear medicine. So nuclear medicine, we measure most of our stuff in millicuries. So milli, understand that milli means thousandth, but it's to the small end, right? So it's usually 10 to the negative third. So milli is going small. Micro is 10 to the sixth, so it's smaller than milli. Sometimes we measure things in microcuries, millicuries and microcuries. You rarely measure something as a curie. So you remember that it's to the negative third and to the negative sixth. The other one is a good one to know is giga. When you talk about becquerels, you'll usually see something coming in gigabecquerels, and remember that giga means a billion, so that's 9 places or 9 zeros typically. Those are good ones to remember, but just kind of understand what we mean here when we say these terms, especially those 3. Radioactive terms that you'll hear in nuclear medicine, there's old terms and there's new terms. So when we talk about exposure dose and dose equivalent, which I won't define those right now, some of you already know that from X-ray, but you'll hear things like the Renkt and the rad and the rem are the old units. They're we say old, what we mean is American units, and the standard international unit, which is SI unit, is the column gray and the sievert. What you may be asked or may need to know in your as you practice is that 100 of the old equals 1 of the new. That's how you convert between these two. So if you're talking about exposure and you're talking about rad, and you measure something and you have 100 rads, that's just going to be 1 gray. Or if you have 1 gray, that's going to be 100 rads. And so you would just move 2 decimal places for those. So just think of it that way. When we talk about radioactivity, the American unit is the Curie, named after Madame Curie, who was a scientist that was instrumental in discovering and understanding radioactivity and radiation. The becquerel is the standard international unit. Most of the time in the United States, we're still working with curies. And so you will see the millicurie and the microcurie. But you may have some things that come in becquerel. Like we have I've worked and seen things come in becquerel. This conversion, 100 of old and 1 new, does not apply to radioactivity. It's only for these exposure, dose, and dose equivalent. So what I want to show you real quick is the conversion to go from Curie to becquerel. So the way that this is measured, Curie, 1 Curie equals 37 billion disintegrations per second. Okay, now the reason that, let me just define it this way. A Curie was named after Madame Curie. What they did is they took radium, and she measured radium, and she measured radium for a certain amount of time, and it gave us off this many disintegrations of radiation, and they just named that 1 Curie. So it's very abstract. It doesn't have a specific meaning, but they define it in terms of this many disintegrations per second. Okay, becquerels, when they changed to the standard international unit, they said that 1 disintegration per second is 1 becquerel. So you have this massive difference between what is a Curie and what is a becquerel. So one of the equations to look at and think about is that 1 Curie is equal to 3.7 times 10 to the 10th becquerels. That's what's represented up here. Okay, so just to give you an example, if we did that out, I would say, what if I had 2 Curies, right? And so I would times this first number by 2. So 2 times 3.7 times 10 to the 10th becquerel. On this side, I would get 7.4 times 10 to the 10th becquerel. That would equal 74 billion becquerels. Now what I've done here, this is why we work with gigabecquerels and we don't typically say something in becquerels, because giga represents billion, remember? So it's easier when you're going from Curies to becquerels, because there's so many becquerels in 1 Curie, we can just say 74 gigabecquerel. So 1 Curie equals 3.7 times 10 to the 10th becquerel. You could also say 1 Curie equals 37 gigabecquerel, which is billion becquerels. And that's what I've written down here. So know this equation to say 1 Curie to how many becquerels, but understand that you'll probably say 1 Curie equals 37 gigabecquerels. Now, when we go back the other way, it doesn't work. And it's because of what I told you at the beginning. A Curie is based on a gram of radium, and a becquerel is just based on 1 disintegration. So it's not an equation that flips like it normally does. So you kind of have to learn 2 equations. If you're going to go from Curie to becquerel, you're going to use this one. You're going to 1 becquerel, 1 Curie equals 37 gigabecquerels, or you can use it right here as doing it in scientific notation is easier for you.
Can I ask a really quick question?
Absolutely.
Maybe the brain is fried, but
Brain
I'm
is
not
fried.
understanding how we did the conversion from becquerels to gigs. Is that right?
Yep. Thank you for asking. Great question. I guarantee other people have the question. So sorry about that. Yeah, no problem at all. So forget this middle part where I said you multiplied it by 2, and let's just look at 1 becquerel. So I said that 1 becquerel is 3.7 times 10 to the negative, or 10 to the 10th, right? Becquerels. So if you multiply that out, it means you do 3.7. So 10 times 10 times 10 times 10 times 10 times 10 times 10. It gives you 10 zeros. So all you have to do is, with scientific notation, start where your 0 is, and then go 10 places to the right because we're getting bigger. So 3.7, I just went, let's just do it over here. 3.7, I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I have 37 billion of them, right? Because one Curie is 37 billion becquerels, but a giga represents billion. So I can say I have 30 billion, or I can say I have 37 gigabecquerels. So in other words, I took all of these zeros, these 9 zeros, and I can just say 37 gigabecquerel. If you go back to here, when we say giga, notice there it's 10 to the 9th. That's where you get your 9 zeros. Okay, so I just was able to eliminate these 9 zeros and say 37 gigabecquerels. Does that make more sense?
Yeah, no, it was just a matter of conversion. I completely missed it. Thank you very
No
much.
worry, no worry. And this is why this is sort of confusing. I wish it were easier. And in practice, you're probably not gonna have to sit down and do this. You could use, there's calculators out there. But you may be asked to understand or make a conversion on your board. So 1 curie equals 37 gigabecquerels, or 1 curie equals 37 billion becquerels. Does that make more sense?
Yes, thank you very much.
No problem. So now we're going the other way again because of this weight factor based on a gram of radium. It changes. So the equation that you come to when you talk about becquerels to curies, and I'll try to be succinct with this because it gets even a little more confusing than that one. So 1 becquerel is equal to 2.7 times 10 to the negative 11th curies. Okay, so we've gone small now. I wrote that down here. Okay, so negative 11th, if we start with 2.7 right here, we counted over and we had to go 11 places over. Okay, that is a number that you would never, you know, if you get something and it's in becquerels, you would never say, I've got 0.0000002 curies that I'm going to give my patient. You're never going to hear that. You're going to hear something reported in millicuries. So the question becomes, how do we get then from a becquerel to a millicurie? This is still true. You can do this no matter what. You can say 1 becquerel equals 2.7 times 10 to the negative 11 curies. Okay. The other thing you could do is you could change and go back to saying, well, what if we use giga on our becquerels? Because remember, becquerels are huge in their number compared to the curie, which is like 1 in its number. So if we go ahead and change our equation, we could say I have 1 gigabecquerel equals 2.7 times 10 to the negative 2. Now, how did I get negative 2 from 11? Well, remember, giga represents billion, and it's 9 placements or 9 zeros. So if I take my negative 11 and subtract 9, I'm down to just negative 2. So now I can say, and again, this is another equation that you can use, and likely the one that you will use, is 1 gigabecquerel equals 2.7 times 10 to the negative 2 curies. Okay, but I wanted to show you how I got there, because if we go becquerel to curie, we have this massive number. We're starting to make it smaller and more workable if we say gigabecquerel to curie. And then I gave an example down here, right? So if you actually did the multiplication and you said 2.7 times 10 to the negative 2, so you have 10, we're going to go negative 2, we'd go over 1, 2 places, and that's what you get down here. So 1 gigabecquerel is 0.027 curies. Now, again, you're still not going to do that in practice because we don't report things in curies. If you've been to your clinical site so far, they're doing stuff in millicuries, right? Like a bone dose is, for a bone scan, you might use 20 or 25 millicuries. You're never going to use curies, and it's because we don't want to work with decimals. So the thing to correct on that side, and again, I know this gets confusing, and that's why you're going to have to look at this a couple times. But what we said is, what if we use millicuries? I'm going to go back again to try to make this obvious. If we go to millicuries, it's 3 decimal places. So going from a curie down to a millicurie is 3, right? It's 10 to the negative 3rd. So, so if we go here and we say we're going to change that and go down 3 places and make it in millicuries, we go 1, 2, 3, and now we have 27 millicuries. Okay, so now I'm going to get to a final other equality or equation you can look at. I actually put these in last night. It was one of the things I added, so you can notate it on yours. It's not on yours right now, but because I realize this is a confusing concept. So now 1 gigabecquerel equals 27 millicuries. Now you could use that if you were given 5 gigabecquerels. All you got to do is times that by 27, and you get however many millicuries. It depends on what the test asks you. If it goes from becquerel to curie, if you're going from gigabecquerel to curie, or if you're going gigabecquerel to millicuries. So I know that is super confusing. It's tough. You have to kind of think about it. I would memorize this equation for curies to becquerels. I would memorize this, and I would memorize this. For the other one, I would memorize this And I would probably memorize this for a short, easy answer. Okay, super confusing. You have a couple of those. I think I put one in, I think there's one of them in the test that you'll have to do. But just study those and try to get those in your head. Memorize some equations. I'm sorry it's difficult. They're just kind of a pain. Okay. We only have like 4 slides left. This slide, when it comes to math, I know that one was confusing. This one looks confusing, but it's going to be way more simple, and you're going to become a pro at doing radioactive decay equation formula. This will be on your boards. Guaranteed you'll have to do decay formula on your boards. I will go over this because we're talking about radioactive decay. Shauna will probably cover it too, and she'll cover the same equation. Between the both of us, I think we pretty much do it the same way, but if there's slight differences, it gives you guys an opportunity to see a couple of different ways you can do it. I need you guys to just trust me, okay? I'm gonna try to explain every portion of this equation. When I saw this the first time, I thought it looked like a different language. But I'm gonna explain the parts of the equation, and then I'm gonna show you how to plug in, based on what you'll need to do. I'm gonna show you how to plug in the portions of the equation and how to do every type of problem that you'll get in a decay formula answer, okay? So remember, when we're talking about radioactive decay, what might happen here is you might get a question that says, you have 10 millicuries. What will that 10 millicuries be 4 hours later? What will be the dose? Okay, so you're going to learn how to be able to calculate radioactive decay. So let me define what these parts of the equation are. So activity equals the original activity, that's the subscript O, times the logarithm of negative lambda times time. If it sounds like I spoke a different language, let's go back. Don't worry, you will get this. So activity would be your original activity. So if I said I have 10 millicuries, what will it be in 2 hours? Then my original activity would be 10 millicuries, and my activity would be what I'm trying to solve for, okay? If I said I have this much now, what will it be? Well, let me put that out. Just original activity is always the original one that it gives you. And I'll work that out better when we show you an actual problem, okay? So original activity, that's what this represents. Activity equals the original activity times by the log. What's a log? What the heck is a log? Logarithm represents what's called exponential function. So an exponential either means something is getting exponentially bigger, or in our case, something's getting exponentially smaller. So think about something like, you know, back in the day when we were all dealing with COVID, right? So if you had a person that had COVID, they could get, let's just say arbitrarily, they could get 5 people sick. And then those 5 people get 5 people sick, right? So you'd have exponential growth. Something is getting larger and larger each time it grows. So that's exponential growth. We in nuclear medicine are talking about exponential decay, something getting exponentially smaller each half-life that it has, right? So that's what the logarithm will represent in our equation. Then the lambda is what's called decay constant. So E represents the exponential nature of radioactive decay, but lambda represents the fact that it's constantly happening. And radioactive decay happens at a constant rate, right? That's why we can make an equation, we can measure it, we can know what it's going to be in 5 hours, because it happens at a constant. Lambda is defined as what you see here. It's 0.693 over whatever the half-life of your nuclide is, whatever nuclide you're working with, okay? 0.693 is what's called Euler's constant. And Euler was a mathematician scientist that came up with a way of representing a number, something that happens at a constant rate. You won't be tested on that, don't worry about that. Just memorize that it's 0.693. No matter what equation you're doing, what you're working with, what radioactivity you're working with, however much time it's been, you're always going to use 0.693. So put that in your head, 0.693, 0.693. You'll do enough of these that you'll remember that over half-life, okay? So the negative part of this is, again, because we're decay, we're going smaller, not bigger, okay? So now let me scratch a little bit of this confusing off and we'll put it into the actual one that I want you to memorize. I want you to memorize this equation. activity equals original activity times by the log of negative 0.693 over half-life times time. This needs to be memorized. And I will tell you, you're going to do enough of these between now and when you're done that you'll memorize it just by doing them all. But this equation is what you need to know. I will teach you how to work this equation, and all you'll have to know is where to plug in what. Okay? Now, the things that we're going to be able to get or solve using this equation is we're going to be able to solve for activity. We're going to be able to solve for original activity. We're going to be able to solve for time. And then we're going to be able to solve for half-life. Okay? Those are the 4 things that we solve for in this. There's a couple of functions you need to find on your calculator. So the first one is the logarithm function, which is usually most calculators represented as an e or an e to the x function. Okay? If you take your iPhone and you go onto the calculator, whoops, that's the camera. And you have it the normal way like that, and you turn it, it becomes scientific, and that e to the x is on here. It's just kind of right there in the middle. But whatever calculator you're using, whatever scientific calculator, find that e to the x function. Whenever we're solving for activity or original activity, we're going to use that e to the x logarithm function. The other one that you'll need to find is an ln function, which is called natural log, and it's kind of the opposite of the logarithm function. Whenever we're solving for time or half-life, we'll use this ln function. Okay. Now, I got 4 examples we're going to go through, and then I'll let you guys get out of here. And I will have this information and similar what I'm saying on this, and I will also have it broken apart by itself on a previous lecture that I did for you to look at on Canvas. Okay, let's try to make all this gibberish make some sense. Here's what I want you to think. These things to remember are super important. Okay, we want to get our answer right the first time. That's the first. I know of course you want to do that. Why would I write that down? ARRT uses the Windows Scientific Calculator. So if you have Windows, it might be helpful to pull up the Windows so you can find the calculator and find the functions on it. Those are kind of tips. The third one is something that I just would highly advise that you always write down the formula. When you've got a radioactive problem, just write down the formula, because then all you have to do is identify the parts and plug them in. When I took my boards, the first thing I did when I sat down on their scratch piece of paper is I wrote out the formula. In my days of memorizing were over. I thought, yes, I'm writing this down and I'm forgetting it. I have it with me. Okay, so always write down the formula. And then the other thing you're going to want to do is write down the quantities. So what I do is I write down the formula, and then I write the different parts, the activity, original activity, time, and half-life, and I fill those in, and I find out what I have and what I need to solve for. Okay. You're also going to want to note if you need to figure out millicuries or microcuries or days or hours, so you can have the right answer at the end. Fill in what you know, calculate for what you don't know, and at the end, you're always going to want to ask yourself, does this answer make sense? And we'll do that when we finish here. Okay, is it logical? Is it reasonable? So here's our first one. It says you measure a technetium-99m dose at 10 millicuries. What will the dose measure in 2 hours? Okay, so our original activity is going to be 10 millicuries because it's the dose that the original dose was starting with. The activity that we're going to have in 2 hours is going to be our activity. Okay, so original activity is 10 millicuries. We don't know what it will be in 2 hours. We do know that our time, which is represented here on the equation, is 2 hours because it defined that. We're talking about 2 hours of time. And then it told us we were using technetium-99. Technetium-99 has a 6-hour half-life, so we know it's 6 hours. Okay, memorize that tech has a 6-hour half-life. You're going to get that just from working in your nuclear medicine department and doing your clinicals. 6-hour half-life. Look at other ones. When I've given you them on a test or anything like that, I will identify what you're using and what its half-life is. For now, you're going to have those memorized by the time you're done with this. But for now, technetium is a 6-hour half-life. That's the only one I don't identify, I think, but just know that. Okay. All right. So let's start plugging in our equation. We don't know what the original activity is, or the activity that we're looking for is, but we do know the original activity. So we're going to put that in 10 millicuries times by the log of negative 0.693 times by 2 hours. So we plugged in 2 hours. And then we know that it's over half-life, which is tech, so we put 6 hours. I crossed out the hours because they're the same on top and bottom, and we can just work with numbers. So how do I start to solve this equation? Well, as with any algebra, you see what you can solve on which side of the equation. Since we have our a alone on its side of the equation, there's nothing we can do there. We have to, because this logarithm is here, we have to start solving the right side portion. Now this logarithm, everything up here is basically like the exponent to the logarithm, okay? So because we have everything filled out here, this is where we can start. So we can go and we can grab our calculator and say negative 0.693 times 2 divided by 6. When I plugged that into my calculator, I got negative 0.231. So now my equation reads A equals 10 millicuries times the log of negative 0.231, okay? So now at this point, you're gonna find that e to the x on your calculator. What you'll do is you'll write in your calculator negative 0.231 and you'll hit this e to the x button. What that does is it's going to get rid of your logarithm and take that logarithm with exponent out of logarithm form and into a normal number. So when I took negative 0.0231 and I clicked that button on my calculator, what I got was 0.794. So now my equation reads A equals 10 millicuries times 0.794. Now you have a super basic algebra equation, right? So in this case, what you would do is you would times that 0.794 times 10 millicuries, and you get A equals 7.9 millicuries. Okay, now I'm going to point out a couple of things. One is that I usually will just take my 3 decimals out. When you're doing your tests, just know that I've calculated the test to be about 3 decimals out. And again, I've given you that window like we talked about earlier, but about 3 decimals out. So that's the first thing I'll say, is notice that I used about 3 decimals. I'm asking myself at the end, is this logical or reasonable? Okay, I had 10 millicuries, and I know that every 6 hours it's half gone. So if I went 6 hours out, I would have 5 millicuries. So I haven't gone all that way. I've only gone 2 hours out. So does it make sense that I would have 7.9 millicuries? I think it makes sense, right? I expect it to be a little smaller than 10, but not quite half. So that makes sense to me. That's logical. It's reasonable. It makes sense. If I were to come down here and I got like 79 millicuries, I'd have to be like, wait a minute, I did something wrong, because there's no way that 10 millicuries getting smaller with radiation is going to somehow equal 79 on the other end, right? So just ask yourself that. It's going to help you from making mistakes. I don't care so much in the homework. You can actually do the problems again and again if you want till you get them right. I haven't put a limit on it. But in your boards, you don't want to make that a dumb mistake like that, right? So again, when you're finished, get in the habit of asking yourself, did that make sense? Did I put in the right factors and does that make sense? Okay. So that's one where we were solving for activity. The next one, we're going to solve for original activity. So this is how it might be worded. Something like this. You measure a Tech99M dose at 10 millicuries. What was the dose measuring 30 minutes ago? Okay, so now you're measuring it at 10, but it wants to know what it was before. So the way to think about this is that now my activity is what I have right now in front of me. My original activity is what it was 30 minutes ago. So you kind of just have to pay attention to what it's asking, because I wouldn't want to put this 10 millicuries as my original activity, because my original activity would have been what it started at when it was the greatest, right? And maybe that's the way to think of it, is say, okay, when my dose was the biggest, that's really the original activity, right? And so in this case, my 10 millicuries 30 minutes ago would have been bigger, right? So that's my original, or yeah, or sorry, I said that wrong. My 10 millicuries 30 minutes ago would have been my original, or activity. No, you know what? I might have put this wrong for you guys. Hold on, hold the fort. You measure a 10 millicuries. What was the dose measuring 30 minutes ago? Yeah, so 10 millicuries is your activity now. The original one was what you're looking for. Sorry, I'm tired too. I'm sorry when I confuse you and it's late. So let's plug in the factors, okay? So we have our 10 millicuries now, which is our activity now. We've written our equation, activity equals original activity times the log of negative 0.693 over half-life times time. 10 millicuries is our activity. We don't know our original activity. Our half-life, now this is interesting, is 30 minutes, okay? And I put this in here on purpose as a teaching tool. Pay attention to what it's asking you. It's asking for 30 minutes, okay? We know it's tech, so our half-life is 6 hours. Now, when I plug this in, I'm going to plug in my 10 for activity that I have now. Don't know the original, times the log of 0.693. Now in time, you can't put 30 minutes. Your time and your half-life have to be the same values that you're looking for. It doesn't matter if you put it in minutes, that's fine, or if you choose to go hours. But I put this in here because you could have that on your boards. You need to pay attention. These have to be like terms, okay? So they're both in hours. I can't put 30 minutes. So in this case, I chose to change it to hours. So it's 0.5 hours, which represents half an hour or 30 minutes. If you wanted to go to 30 minutes, you could. You could leave this 30 minutes, but then you need to translate 6 hours into minutes. In that case, you'd have 360 minutes. No, yeah, or 360. No, you would have 3,600 minutes. So again, see how that can get hairy. I chose mine to be 0.5 hours. That was easier in my brain. Okay, so I had to put it in that way. So now I've got my equation here and I can start to solve. So again, with an equation that looks like this, and you're trying to solve either of these two, we can start on this kind of exponent side of the equation. So in this case, I'm going to take in my calculator and do negative 0.693 times 0.5 divided by 6. When I do that, I get negative 0.05775. If you just included 77, that's fine. You'll get a good enough answer. Now I have my equation that looks like 10 millicuries equals the original activity times the log of negative 0.05775. So now I'm going to take that E function on my calculator. I'm going to take this number as a regular number. So I just, in my calculator, I'm going to hit negative 0.05775, and then I hit the E to the X function. When I do that, that takes it out of the logarithm and makes it a normal number. So now my equation is 10 millicuries equals the original activity times by 0.9439. Okay, now I can solve a normal algebra equation. So in this case, we need to get rid of have A by itself, A to the original activity by itself. So with this, I'm timesing it by 0.9439. So what I'm going to do is divide both sides by that to get rid of it. On the right side of the equation, when we divide by 0.9439, we can cancel out. On the left side of the equation, we end up with 10 millicuries divided by 0.9439 equals original activity. When I do the math here and I say 10 millicuries divided by here, I'm going to get 10.6 millicuries equals the original activity. So I need to ask myself, I have 10 millicuries that I'm measuring now, and I want to know what it was 30 minutes ago. So 30 minutes ago, it was going to be a little bit bigger. It's only 30 minutes. Remember, this is a 6-hour half-life, so it hasn't been very much time. So to me, it makes sense that it would just be a little bigger than what I'm measuring, 10.6. That makes sense. If it was smaller, if you came up with like 9 millicuries, that you'd have to logically say that doesn't make sense because it would have had to have been bigger before, right? Because it's decayed and gotten smaller. So ask yourself those questions at the end. 2 more examples and then we'll let you get out of here. And I usually won't ever go quite this long, sorry. Okay, so the next one is now we've solved for activity and we've solved for original activity. Now we're going to get into how you solve for time and for half-life. So for this one, it might say something like a dose of tech originally measured 100 millicuries, but now it measures 9 millicuries. How much time has elapsed from the original measurement? Okay, so this one's pretty easy because it says originally it was 100, so we know that our original activity is 100. It measures 9 now. We have our half-life because it's tech, we know that's 6 hours. What we don't know, and what it's asking us is how much time has elapsed, okay? So I take all of that and I plug it into my equation. Activity is 9 millicuries, original activity is 100 millicuries, times by the log of negative 0.693 times t, because we don't know what time is, all over the 6 hours. Okay, because we know that's our half-life. So this is going to be a little different on how you work this out. When we have an unknown factor over on the logarithm side, we cannot do anything with it yet. Okay, so what we have to do is look to other areas of the equation that we can start with. The logarithm, we notice, is being times multiplied by 100. So we can get rid of and try to get that 100 out of here, and that's what we want to do. So because this side of the equation is being multiplied by 100, the way that we could get rid of it is we could multiply the right side of the equation by 100. We could also multiply the left side of the equation by 100. When we multiply the right side of the equation by 100, it gets rid of the 100 millicuries because they cancel out. And on the left side of the equation, we end up with 9 divided by the 100 millicuries equals the log of negative 0.0693 times time over 6 hours. Okay, now we can't do a logarithm function of any kind. The other problem is you can't have a variable and you can't have a negative in the logarithm side and actually solve anything with it. So at least not with a variable. When all the numbers are in here, it's no problem. When there's a variable, we can't have a negative. So what we're going to want to do, if you remember back to your algebra days, how do we get rid of negative on one side of a fraction, on one side of the equation if we're dealing with fractions? Well, the algebraic principle is that if you flip the opposite side of the equation and make a fraction of the opposite side, then it gets rid of the negative on the other side of the equation. So that's what you have to do, okay? So we had our 9 over 100. So what we're going to do is we're going to flip that and we're going to make it 100 over 9 now equals the log of positive 0.693 times time over 6 hours, okay? Now we have an equation that we can use our ln function to solve because it's positive. Can't use the ln function and get out of the e if we don't have if we have a negative, sorry. So again, we're going to be able to use this ln function, but we got to make this right side positive. The way you make the right side positive is you flip the left side, okay? That's why I left this in equation form too. I didn't just do 9 divided by 100 quite yet. I left it the equation because I knew I was going to flip the equation. So now we're here, we have 100 over 9 equals the positive side of this logarithm. Now, what you're going to do is now use the ln function on your calculator. You don't do the ln function to the logarithm side because ln function represents kind of the opposite of logarithm. So the only number that we can do it to is the other side of the equation. So at this point, you're going to take 100 divided by 9. When I did 100 divided by 9 in my calculator, I got 11.11. Okay, so we have 11.11 is equal to the log of 0.693 times time over half-life, which is 6 hours. Now we can use our ln function. You're going to apply the ln function to the number that is on the left side of your equation, the opposite side of the logarithm, okay? So when I did that, I just took, in my calculator, I put 11.11, and then I hit the ln function, and that gave me 2.408. So what that does is it gets us out of our logarithm. So now our function, or now our equation is 2.408 equals, and again, we got rid of the logarithm, so it just simply equals 0.693 over half-life times time. Okay, so now you have a very normal algebra equation you can use here. Okay, very normal algebra equation. I didn't show the solving on this, but just to walk you through it in your head real quick. First thing I would have to do on this equation is I want to get out of this fraction over here. And so this side is to be being divided by 6. If I want to get rid of the 6, I've got it, it's being divided, so I have to multiply by 6. So I would multiply this side by 6 and it would cancel out. And then I would multiply this side by 6. And then I would have a number that was equal to 0.693 times time, and then I can solve it algebraically. If you don't understand that, let me know, and we can work on algebra too, but you should know how to solve that from algebra. When I did the solving, I ended up getting t equals 20.8 hours. And so now again, I'm going to ask myself, is this logical? I started out with 100 millicuries. Every 6 hours, it goes half. And I'm saying it's been about 20 hours. Is that logical? It's logical because in 6 hours it'd be 50. In 12 hours, you're going to be at 25. Another 6 hours on top of that, you're going to be at what, 12 and a half. So it's logical that if it's at 9 millicuries, it's been 20 hours. Okay. This is a little more complicated. So look at this a few times. It's a little more complicated than the other one. But just remember that you're going to want to get rid of the negative by flipping the fraction. And then you're going to be able to get rid of your logarithm by applying it to the left side of the equation with the ln function. And that will break it to a normal algebra equation. Let's do one more, and this time we're going to solve for half-life. So this one might say something like a nuclide has an activity of 20 millicuries. So notice I said a nuclide, you don't know which one it is. A nuclide has an activity of 20 millicuries. 40 days later, the activity is 640 microcuries. What nuclide is it? Okay, so again, a little bit more convoluted. I did this on purpose, okay, guys, because you can get questions like this. And this makes sense, because if you have 20 millicuries of something, 40 days later, it's probably going to be in the microcurie range. So to change from micro to milli, you need to go back to those where we talked about the exponent, right? So milli is 1,000, so it's going to change by 1,000. So in this case, if the decimal's right here on 640, you'll go 1, 2, 3 decimal places, and that gives you 0.64 millicuries. Okay, so be aware of that. If something asks you, has 2 different things, we got to have matching. And the last one I purposely did 30 minutes and 6 hours. We had to shift them to hours. This one's the same thing. They've got to be the same. So you've either got to convert 20 millicuries to microcuries, or you've got to convert the 640 microcuries to millicuries. That's what I did here. Is I converted to the millicuries. Okay, so I plugged everything into my equation on this first portion. I originally plugged it in as the microcuries just to have my factors written out. So 640 microcuries, the 20 millicuries was my original activity, and then 40 days is my time. And I don't know my half-life because it just says a nuclide. We don't know what nuclide that is, so I don't know the half-life, right? In the next part of the equation, what I did is I just converted. So I have 0.64 millicuries now and 20 millicuries. Now that these are the same, I can get rid of the millicuries. So now this is our equation that we're kind of going to solve for. Now, again, you'll notice here that I can't really do anything over here because I can't use my ln function to figure this out. I've got a negative. So what can I do? Well, this side of the equation is being times by 20 millicuries. So if I want to get rid of it, I'm going to do the opposite. I'm going to divide this side by 20 millicuries. In algebra, when we do something on one side, we have to do it on the other side. So if I divide this side by 20, it gets rid of the 20 millicuries. If I divide the other side by 20, I'm going to have 0.64 divided by 20 now equals the log of negative 0.693 times over half-life times the 40 days. Okay. Now remember, same thing as the last one, I can't use the ln function when I have a negative in my exponent value, or excuse me, in my my e value. So what I'm going to want to do then is I'm going to want to get rid of that negative by flipping the other side of the equation. Okay, so when I flip the other side of the equation, I end up with 20 over 0.64 equals the positive logarithm this time of 0.693 over half-life times the 40 days. Okay, so now that I'm at this state, I can do the division on the left-hand side. When I do 20 divided by 0.64, I get 31.25 is equal to the positive logarithm of 0.693 times 40 days over half-life. Now I'm ready to use my ln function. What do I use the ln function on? I use it on this whole number that's on the left. Okay, I use it on the 31.25. So all you've got to do, take your calculator, put 31.25, hit the ln button. When I did that on my calculator, it gave me 3.44. So now I have a very normal equation. 3.44 is equal to 0.693 times the 40 days all over the half-life. Now we're back down to just a normal algebra equation. Okay. For me, you could do a couple of things here. Again, if you need help with the algebra, let me know. But You could put 3.44 over 1 and you could cross multiply these things to get t1/2 by itself. The other thing you could do is you could multiply both sides by t1/2, and that would bring t1/2 over here times 3.4, and then you solve the algebra from there. If you don't know how to do that, let me know. I'm gonna leave that right there just for, because we're way over already anyway. But when I did the normal algebra here, I ended up with t1/2 equals 8.05 days, which consequently is the half-life of I-131, okay? So I have to ask myself, is this logical? I started with 20 millicuries, and 40 days later, I ended up with 640 microcuries. That makes sense, because again, this has an 8.05 day, or an 8.05 day half-life, okay? So that makes sense. It's been 40 days, quite a bit of time. Several half-lives have occurred. So that makes sense and it's logical. Okay, that's the last example I have. The only other tip I'm gonna give you is you're gonna run into one other thing on your homework. It may ask you about percentages. So the only thing I want you to think with percentages is if it says, I have an isotope, let's say I have tech, and it asks you, what do you have? Well, let me see, let me think how it might be worded. Well, I'll just say this, instead of giving you an example, let me just give you I'll just be straight, so then I confuse you less. Activity and original activity, if it's asking for a percentage of something, like what percent is left over of something, original activity will always be 100%. Because whatever it originally was, it's 100% of it, right? So if you're trying to figure out, and it tells you you have 100% of something, how much percentage will you have of that thing in 8 hours? And it's tech. But then all you have to do is say, I know what original activity is 100%. I'm trying to solve for what 30%. When will it be 30% gone? Something like that. Okay. So if it asks for percentage, just realize that 100% is always going to be your original activity, because wherever you started at originally is 100% of that thing, right? So that's the only kind of curveball that you might see that might be a little confusing. So just remember, 100% is original activity, and then any other percentage that it gives you is activity. Okay. And after that long grueling time, I am done. That's all I have got for you. Let me stop sharing my slides. I'm happy to stay for a couple more minutes. If there's any burning questions, I know you guys are probably fried. So I hope you look at this again when you have some more time. I'm sure you're fried from this whole day. So again, I will post radioactive decay by itself, talk about that on Canvas, and then I'll get this posted on Canvas. It takes about an hour for it to render, and then I'll try to get it on later tonight or by tomorrow morning or afternoon. I'll try to be very quick about it. Any questions of those of you that survived? I know that you are overwhelmed. I was too. You'll get this. It's okay to be overwhelmed. You will get this. This is new language, totally. The math and the physics. But you'll get it. Hang in there, okay, guys? All right. Let me check messages real quick to make sure nobody else posted anything there that we need to hurry and talk about. If not, study. I will see you next time, and take your test between now and then. And let me know if there's any questions. Again, remember to message me on Canvas is the best way. Okay. All right. Thanks all.
If I can I ask you a question?
Yes.
So the PET CT book, that's 8th edition, that's acceptable? Because
Yes.
that 9th edition sold out everywhere.
100% acceptable.
Aside from online, but I don't want an online version.
Yeah, no, yeah, it will work just fine for you.
Okay, thank you very much for your time. Please enjoy your night.
Of course, no problem. You too. Hey, we'll see you tomorrow. Actually, I didn't think about that, but we have the orientation tomorrow. I'll be on there. I probably won't say a whole lot, but I'll be on there. So see you guys later.
See ya. Thank you.
You're welcome.